Why use nonlinear amplification in analog signal processing? Imagine trying to turn up the volume on a speaker and suddenly hearing a distorted, gritty sound instead of clear music. That's what nonlinear amplification can do in certain situations. It might sound counterintuitive, but in some cases, using nonlinear amplifiers actually makes systems work better. Most amplifiers are designed to be linear, meaning they increase the signal strength evenly without changing its shape. But in real-world applications, signals don't always fit neatly into that pattern. Sometimes signals are very strong or very weak, and linear amplifiers struggle to handle this wide range without distortion. That's where nonlinear amplifiers come in handy. They don't keep a constant ratio between input and output. Instead, their gain depends on the signal's amplitude or other factors. This can cause distortion, but in many cases, that distortion is either harmless or even useful. One big reason to use nonlinear amplification is efficiency. Nonlinear amplifiers like Class C types only conduct current during part of the signal cycle. This means they waste less power and generate less heat. They are perfect for devices that run on batteries or for radio frequency transmitters, where saving energy is important. Using these amplifiers helps extend battery life and reduces operational costs. Another reason is matching the behavior of certain sensors. Some sensors, like thermocouples, produce signals that are naturally nonlinear. If you use a linear amplifier, you won't get an accurate reading. Nonlinear amplifiers can be designed to match the sensor's response, making the signal easier to interpret without extra digital processing. Protection is also a key factor. Sometimes signals can get too large and damage components. Limiting amplifiers, which intentionally distort the signal by clipping peaks, help keep signals within safe levels. This prevents damage and keeps the system running smoothly. They can be designed for sharp or gentle clipping, depending on how much distortion is acceptable. Handling signals with a wide range of amplitudes is another reason. Some signals can be very small or very large. Linear amplifiers might distort large signals or not boost small ones enough. Logarithmic amplifiers compress the dynamic range, making it easier to process these signals without losing important information. Frequency multiplication is another use. Nonlinear devices generate harmonics, or multiples, of the input frequency. By amplifying specific harmonics, engineers can create high-frequency signals from lower ones. This technique is common in radio and microwave systems to generate carrier waves or local oscillators. In real-world applications, nonlinear amplifiers are everywhere. In communications, they are used for frequency modulation signals like FM radio, where the information is carried in frequency or phase, not amplitude. This makes transmission more efficient. In musical instruments like electric guitars, nonlinear stages produce harmonic distortion that shapes the sound. In sensors and instrumentation, they help condition signals from nonlinear sources, making measurements more accurate. It's important to remember that nonlinear amplification isn't suitable for all signals. If the information depends on amplitude, distortion can corrupt the data. But when amplitude isn't critical or can be controlled, nonlinear amplifiers offer advantages like better efficiency, simpler design, and specific functionalities. They are essential tools for electrical engineers working on systems that need to handle complex signals efficiently and effectively.